Hello, in this lecture we will learn some of the verification methods that are most commonly used. We will learn about simulation-based verification, we will learn about formal verification, we will learn what is semi-formal verification, and we will also learn what are assertions and how assertions are used generally in verification. So let's start with what is simulation-based verification. So this diagram shows a design implementation and a simulator, typically a software simulator surrounding it. So the simulation based verification is the most commonly used verification method for most of the design verifications. In this approach, we use a test vector generator to generate input stimulus to the design, and the design under test or the design implementation is actually simulated using the simulator. We also use a golden reference model or some kind of a checker or a scoreboard to generate the expected outputs, which are treated as the golden outputs, and these are compared against the actual outputs coming from the design implementation to ensure the correctness of the design. Now, based on the complexity of the design's implementation, the test vector generator can be as simple as a directed test generator, or it can also be as complex as like a random or a constrained random test generator. We also use like several approaches like assertions and coverage metrics to make sure the verification is complete and also the quality is met. We'll see most of the details about that in some of the following lectures. Now the next most commonly used verification method is formal verification. So let's see what formal verification is. Formal verification is a method by which we prove or disprove a design implementation against a formal specification or a property. So in this method, we mostly use like mathematical reasoning, or we use like mathematical models or algorithms to prove a design against some kind of a formal specification. In the formal verification uses certain tools which are based on certain algorithms where it kind of exhaustively explores all the possible input value combinations across time, which can exercise your all the various state spaces in your design. Now, this approach works well for small designs, especially when the number of inputs, outputs, and states are small. Whereas as the designs state space start increasing, the formal verification may not be all that effective. Formal verification is again used mostly for two kinds of applications. The first is equivalence checking. Equivalence checking is truly not a functional correctness check, but it's an equivalence checking between like two kinds of implementation. So an equivalence checker can check the logical equivalence or the functional equivalence between a say an RTL implementation as well as a final version of the netlist. That is like one most commonly used application of formal equivalence checking in most of the designs. So let's see, this diagram shows how the equivalence checking is done. So RTL A or gates A is like one kind of a reference or a golden design. Now during implementation, we implement it as like another design on RTL B uh, or gates B. So this can be a design which is like targeted on certain library, or it's kind of modified for certain things. Then we do an equivalence checking between A and B to make sure whether functionally A and B are equivalent. If it doesn't guarantee like both are correct with respect to spec, but then it guarantees like the two kinds of implementations are functionally equivalent. Uh, yeah, so similarly, we can also have say if there's another kind of implementation for the same design from the reference spec, we can also do an equivalence checking between say in this case design C and design B. So yeah, so the next most commonly used application for formal verification is in model checking. So model checking is a way where we exhaustively search for finite state machines for state or property violations. So this approach is used mostly for designs which has like more with designs which are more based on finite state machines. So in this approach, what we do is like we take like two inputs to this algorithm. So one is the actual finite state transition system or an FSM representation of the design, and the other is a formal property representing the specification. So these two inputs are taken to the algorithm, and then the algorithm exhaustively checks for all the input value combinations which can actually violate this finite state machine model. And then if it doesn't find any input value combinations that can violate the finite state machine model, and that's when we tell the finite state machine is like formally verified. So this diagram should explain the concept. So in this case, we have a finite state machine model based design shown here, and then we also implement a formal property for the space formal property specification for the same design. And then these two inputs are taken to this model checking algorithm, which are typically implemented in most of the formal verification tools. And then the tool will algorithmically explore all the possible input values combination that can exercise all the different state space in the design. And then it can come up with counter examples or combinations of input which can fail the design, or if it cannot find out any combination, then that's when we tell that the design is formally verified. Now this shows some of the advantages of formal verification. So formal verification does cover exhaustively all the state spaces. This is something that is very difficult to achieve by simulation, as we need to manually create tests to hit all the combinations. So formal verification also has the advantage that we don't have to generate any input stimulus, since the tool does the generation automatically. We also doesn't need to generate any expected output sequences, unlike in simulation based where we have to create all the checkers or scoreboards or the reference golden outputs. Uh, Also, correctness of design is guaranteed mathematically in formal verification, so that's also an advantage. On the disadvantages, one of the biggest disadvantage is that formal verification is not scalable for larger designs. So with each additional flip-flop doubling the state space, the formal verification tools has to exhaustively cover like more combinations. So this is limited to designs with small state space like interfaces or FSMs where this works well, whereas for larger designs this doesn't really scale well. Also for larger designs, for every specification we need to translate those specifications into some kind of properties in some kind of a property specification language. So that also becomes like harder if the state space keeps increasing. So with both of that, this formal verification approach works well for smaller designs, whereas with larger designs, it doesn't really scale well. That's the main disadvantage. Now let's see what is semi-formal verification. This is supposed to be the best of both simulation and formal worlds. So especially for designs with like larger state space where formal verification cannot be relied alone. So in this approach, what we do is like we initially do simulation-based verification to cover most of the interesting states in the design. And then around those interesting states in the design, we do an exhaustive formal verification to exhaustively cover all the state space around that interesting states. So this approach will help us to cover the larger design state space faster, and it also helps us to find like bugs sitting deep inside the design because we do an exhaustive formal verification around those interesting. Now let's see what is assertion based verification. So let's see what is an assertion. An assertion is a statement about a design's intended behavior that has to be verified. Or in other words, it's a way of capturing a design's intention or a part of a design specification in the form of a property. This property can be used along with your normal dynamic simulation or along with your formal verification to make sure whether that specific intention is being met or not met. So there are several benefits of assertions. One of the benefits being that it improves observability and debuggability of your verification process, because now that design is intention is captured in the form of a property, you know whether exactly that specific property happened or not during your debugs. It improves integration through correct usage checking. So this is a benefit, especially if multiple units are being designed by multiple people, and when those units are being integrated into a top level design, each of the interface assertions for the specific unit will help to make sure that on an integrated level the design still works properly. So it also, with all of these advantages, it does improve the verification efficiency, because a lot of the time that you spend in your debug or testing can be saved. And it can also improve communication. It's another way of capturing some of these intentions, so it does add to your documentation. And as I mentioned, it's kind of useful for both static or simulation-based verification, static verification, as well as in dynamic simulation. Now let's see what are the different assertion types. There are basically two types of assertions. One is an immediate assertion and another is a concurrent assertion. An immediate assertion is something where at any given time we create like a assertion or a property. So in this example where we see like there's an assert on a equals b, otherwise there is an error, it's gone wrong. So this is an immediate assertion because at any given point of time, if a and b are not equal, then that's kind of a violation of the design intention, and then it can give you an error message. A concurrent assertion is basically where you can create like an assertion which can span across time. So in this case, we are writing a property P1, which tells like at passage of clock, disable if and only if reset, otherwise not of B, followed by one cycle C. So what it means is like whenever reset is not asserted, it tells like whenever B is not 1, followed by one cycle C has to be 1, otherwise that's a property, and if that doesn't happen, it's like a failure. So these are two kinds of assertions. Yeah, so basically you can write an assertion on top of that property. The session-based verification, it's a method of verification where the sessions are used. As I mentioned, it can be used in formal verification as well as in dynamic verification. In formal verification, it can be used to specify all the functional requirements and behaviors of the design. Basically, all the formal properties can be written in using assertions. It uses a procedure to prove that all specified properties hold true. So that's what the formal verification does. Assertions can also be used in dynamic simulation. So these properties or assertions become useful for as like checkers during your simulation, and that can also be used as coverage to make sure like those conditions are being hit. So that concludes this lecture. So in summary, we understood about simulation-based verification. So that is still the most commonly used verification method to find most of the bugs. Formal verification is useful in select areas, especially in finite state machine-based designs, and especially when the state space is smaller. And assertions are also a great value add. Those can be useful both in simulation based as well as like functional formal verification. So that's what I have in this lecture. So we'll see more in the following lectures. Thank you.